Hi everyone. So we're going to go on to section 4.4, the method of undetermined coefficients. And I'll tell you right now, you should probably skip 4.5 unless you would rather do it that way. I'm just going to stick with the superposition approach to this. There really isn't any reason to do 4.5 as well. It's just you're doing the same thing just in a different way. And I think for some of you, it just might be confusing to try to do both ways. But this will be the only method that I'm going to use for the method of undetermined coefficients. All right, so here we're solving a non-homogeneous differential equation, right? So we have some nth order differential equation, and instead of equaling 0, it equals some non-zero function g of x, right? So g of x we're assuming is non-zero, not equal to 0. Right. So first we find the complementary solution. So the complementary solution is just what you get when you replace g of x with 0. So you're solving the corresponding homogeneous version that you did in section 4.3. Okay, so that will be part of the solution. The other part will be what's called a particular solution, yp. And that we can find depends on the form of g of x, right? It could also depend on the complementary solution, but right. So there's two versions of this, right? There's two rules here. One rule, right? Regardless of yc, if yc doesn't contain any form that's similar to yp, then the g of x, right, will determine what yp is. The other version, rule 2 here, says that if there's duplication between g of x and the complementary solution, we're going to have to adjust how we get our particular solution. Right. So let's concentrate on just the first rule here. So let's look at an example. Right. Suppose the complementary solution is just let's do c1 cosine of 4x plus c2 sine of 4x, just as an example. And let's suppose that the g of x, right, in other words, the right side of this equation here, is just equal to, how about 2 e to the negative x. Okay, so what we need is the particular solution, the yp here, and since it's just e to the negative x, this is rule 3 already, we just form an exponential, right? So our yp will be of the following form. It's going to be a times e to the negative x, right? So it doesn't matter what the coefficient here is, the 2, right? So yp may or may not equal, a may or may not equal to 2. In fact, it probably won't be 2. Right. But it depends on the equation, and obviously you can work backwards to figure out what the equation was. In fact, maybe we should do that. Let's write down what the original equation was, right? So since this could also come from, e to the 4ix, the original equation was y double prime plus 16y equals g of x, which is 2e to the negative x. Okay, so when you solve the complementary or the homogeneous version, you get this solution, and then for your g of x, you're going to pick yp to be this, right? And then based on, well, maybe we'll just work this out, right? So if this was the original equation here, what would a be? So, right, so we're just going to, since this should solve this equation, we just have to take the two derivatives here. So let's do yp prime. The first derivative is just negative a e to the negative x. And then yp double prime, we get another factor of negative 1, so that makes this, positive a e to the negative x. So it's the same as yp. So plugging that in here, we get a e to the negative x plus 16a e to the negative x equals 2 e to the negative x. So on the left side, it's really just 17 e to the negative x, times a, sorry. Let's go back. So 17a e to the negative x equals 2 e to the negative x. And you can divide both sides by e to the negative x because we know it never equals 0. So that gives us the equation 17a equals 2, which tells me that a has to be 2 over 17. Right? Okay, so I think that actually solves this equation here. The solution to this equation, right? So remember, it's going to be the complete solution will be the complementary solution plus the particular solution, right? So our complete solution y of x will just be the complementary solution, which I already gave you, is c1 cosine of 4x plus c2 sine of 4x. And then plus the particular solution, which is, excuse me, which is a e to the negative x. So 2 over 17 e to the negative x. Okay. So originally, I wasn't going to do an example where we actually have to solve an equation. For now, I really want to concentrate on how to get the yp, how to get the particular solution, or at least the form of it, just based on what the g of x is, right? So once you know g of x and the complementary solution, you should be able to figure out the form of the particular solution. Okay, so let's look at another example of this. So let's see. So example 2. All right, so now let's just suppose the complementary solution is just c1 e to the x plus c2 e to the 3x. And suppose g of x is just, well, we could just do x squared minus 1. Okay, so what is yp? What is our particular solution here? Yp, right? So this is a polynomial, right? And if you look at the very first rule up here, rule 1 up here, if you have a polynomial, try yp to be a polynomial of the same degree. In this case, this is degree 2, this is quadratic. So that tells me that yp should be a x squared plus bx plus c. Okay? Yep, again, you have to include a polynomial of the same degree. So the fact that, you know, there's no x term here doesn't mean there can't be one here, right? So, right. So if we had the original equation, right, you know what to do, right? Plug this into the original equation and then solve for a, b, and c. This was an easy one because there was only one variable a here. In this, you're probably going to get a system of 3 equations and 3 variables, but you know how to solve those. Okay? Right. So let's go on to a maybe slightly harder example here. So example 3. Suppose the complementary solution, and yeah, let's just make it, so how about c1 cosine x plus c2 sine x, and then g of x is, so how about x cubed e to the negative 2x. Okay, so we want to figure out our particular solution, or at least the form of it, right? So, so what could yp be? So just based on the g of x, right? You notice there's no sines or cosines in g of x. That's going to be important later. This is just x cubed e to the negative 2x. So going back up here, we see that we're going to have an exponential, also going to be part of our particular function, but it's multiplied by a polynomial of degree 3. So that means I'm going to have to take a general polynomial function, so ax cubed plus bx squared plus cx plus d, right, times the exponential part, e to the negative 2x. Okay, so that should be my particular solution, or at least the form of it, right? We're not going to solve for a, b, c, and d yet. We just want to figure out the form. So does that make sense, right? We'll try one more. So again, regardless of the g of x, example 4, let's just, regardless of the complementary solution, let's just suppose g of x, and I'll make this as tricky as possible here. How about it's 2x squared plus x sine x minus e to the negative 5x. Okay, so what would our particular solution be in this case? Again, assuming that the complementary solution doesn't contain any terms that look like this, right? So in this case, yp, so we have a polynomial. Well, it's just a monomial. It's another quadratic. So you're going to need ax squared plus bx plus c, right, just for the 2x squared piece. Then let's move on to the x sine x piece. So x is a linear polynomial. Well, it's just a monomial. It's just a single term. But so we need to multiply that by the sine x. So we have, I guess we're up to dx plus e. So that's our generic linear polynomial times sine x. Right? But hang on, because remember, we're going to be taking derivatives of this to plug it into the original, presumably some nth order differential equation. So we're going to need derivatives of sine, which means we also need cosine here. So we're going to have to go on to fx plus g times the cosine of x. In fact, I would have reversed these, but it's fine. As long as you include both the sine and the cosine, then you should be good. So for the negative e to the negative 5x, that's just going to be some constant, I guess we're up to h now, times e to the negative 5x. Okay, so when you have a sum of terms of different types, let me go back to the three different types here. You have polynomials, you have sines and cosines, and then you have exponentials, right? So you just keep combining those terms, right? You just keep adding them until you get to all of them. So so I hope that helps. Again, I don't think as a practical matter, you're going to see anything this complicated. But you know, if they ask for just the form of the particular solution, then this would be the corresponding form. So I hope that helps. Okay, so the next example will be a little more complicated. So now, hang on. So now let's look at the following example. Suppose our complementary solution is, let's just say it's a polynomial. Let's say it's c1 x squared plus c2x plus c3. Okay, and let's suppose our g of x is just 4x minus 9. Okay, so it's linear function. Okay, so ordinarily we would assume that because this is a linear function, we would say that our particular solution should be of the form ax plus b, because that's linear here. Unfortunately, this is not going to work, and some of you may have come across this, especially either in the homework or if you were doing that number 4 on the problem set, you ran into this situation, right? The problem is this also contains an x term and a constant, but so does the complementary solution. So you can't have this sort of conflict or interference, right? You cannot duplicate terms in the particular solution that are already in the complementary solution. So that's our second rule here, right? So in this case, so how do we resolve that, right? So obviously we know that doesn't work. So what does work here is the following, right? So this says that we're going to have to multiply what we ordinarily would think of as the particular solution by x to some power n. And that n is the smallest positive integer that eliminates the duplication, right? So this is going to be x to some power times ax plus b, right? And what would eliminate the duplication here? Well, if this is degree 2, we need to go one higher than that. We need to make this x to the 3 now. Make it look like an x. So this is x to the power 3. And that should eliminate the duplication. Okay, so that should be our particular solution in this case, right, when g of x is 4x minus 9. And, you can multiply it out, and just to see, you get ax to the 4 plus bx to the 3. And you can see that powers of 3 and 4 do not conflict with powers of 2, 1, or 0. Right? So now there's no duplication. Does that sort of make sense here? Yeah, so let's do another example and see that you do have to look at the complementary solution and make sure that none of these terms match any terms that are in the particular solution. Right? Up until now, the examples we did so far, there was no match, right? Or at least I don't think there was. So let's look at a second example here. Example 2. So let's make our complementary solution yc equal to, so how about e to the 5x times c1 plus c2x. And let's suppose that g of x is equal to 3e to the 5x. Okay, so what would we assume to be our particular solution, right? So regardless of yc, if we didn't know anything about the complementary solution, I would just guess a e to the 5x. That would be our guess for the complementary solution, right? I'm sorry, for the particular solution. Okay. However, if you multiply this out, right, you're going to see c1 e to the 5x, and that interferes with this. That's a conflict, right? That's a duplication. And Rule 2 says you're not allowed any duplications, right? So since this doesn't work, what am I going to do to get the particular solution in this case? Well, again, we're just going to multiply by x to some power, right? So again, our original guess was a e to the 5x. But we can see that that would duplicate part of the solution here. So you might think just multiply by x. Of course, there's also an x e to the 5x in the complementary solution. So that's not going to work either. We have to go one higher than that. We'll have to multiply by x squared to eliminate the duplication. And I'll bring out the a first. So a times x squared e to the 5x. Okay, so that would be the form of the particular solution for example 2. Right? So are we getting the hang of it here? Maybe I'll do one more. And that should do it for 4.4. So example 3 for Rule 2 here, right? Suppose our complementary solution is well, let's say it's c1 plus c2 cosine x plus c3 sine x. And suppose the g of x, the right-hand side of the, the right-hand side here of the original equation, which again, we don't know what the original equation is, but at this point it doesn't matter. We're just trying to find the form of the particular solution. All right. So suppose g of x is, let's just do x minus sine x. Okay. So if that's the g of x, what would our particular solution be? All right, so regardless of the complementary solution, right, let's, ignoring rule 2 here, if we're just using rule 1, I would guess our particular solution should be, again, this is a linear, right, so ax plus b, right? And then we have a sine, so remember we also need a cosine, so c times cosine x plus d times sine x. Right, so that would be my guess. Obviously, if I knew nothing about the complementary solution, that would work here. Unfortunately, that's not going to work because, as you can see, in the complementary solution, we have a c1, which is a constant. That's going to conflict with the b here, because that's a constant. And obviously, both the c2 cosine and the 3c sine, we're going to conflict with the c cosine x plus d sine x here. So all of this is creating a conflict, an interference, or a duplication, if you will. So how do we eliminate the duplication? Right? Well, okay, so yc, or yp rather, the particular solution should have the following form, right? So, so I have to make sure that I don't have a constant here, so I'm going to multiply the ax plus b by just an x. That should do it, right? Because then I get ax squared, which we don't have an x squared here, plus bx, and I don't have an x. So that eliminates the duplication for the first term here, right? What about the sines and cosines, right? So the c cosine x plus d sine x conflicts with this, right? So I need to multiply all of this times, well, in this case, just another x. That should eliminate the duplication now. Cosine x plus d sine x. Okay. And, it might be helpful to multiply all this out, right? You get ax squared plus bx plus cx cosine x plus dx cosine x. Okay. And so that should give you the form of the particular solution for this example. So I hope this helps. And yes, when you do your fifth problem set, that last one is kind of tricky because it involves something like this, where you have a conflict, and so you're going to have to multiply by some power of x, right? It might be just x to the 1, it might be x to the 2. I mean, it might be x to the 3 or something higher, but it's always going to be x to some power n, and n has to be the smallest power that eliminates the duplication, right? So obviously in the first example, we didn't have to use x to the 3. We could have used x to the 4, x to the 5, something higher than that would also eliminate the duplications. But we want it to be as simple as possible. So use the smallest integer, right? Use the 3, right? Or the 2 here, or the 1 here. So I hope that helps. Certainly, if you have any questions, please feel free to send an email on any of this.